as Ruth said, I'm going to start by talking about partially ordered sets, then I'm going to talk about linear extensions, and then we're going to move on to pattern avoidance. So to begin, a partially ordered set, or we'll call them posets in our discussion, is a set accompanied by a binary partial order relation. In our discussion, we'll exclusively be talking about m by n rectangular posets that are represented by an m by n lattice, like the one you see here, where vertices represent our elements and the edges between them represent the partial ordering relation. So as you can see, our lattices turn 45 degrees and we give it an up-down orientation, and we say that element, like an element here, covers this element if it's directly above it and connected. So two elements are related if they're transitively connected through a sequence of vertices and edges. Not all elements have to be related to each other. So for example, this element here and this element here are not related to each other, and that's why it's called a partial ordering. So now we're going to establish some terminology for talking about our posets. It'll be important to be able to refer to the straight chains that span the length and width of our poset, and we're going to call them m and n rows. But before we do that, we need to have a way of referring to them. So we're going to index the elements along the top left and the top right side. So the top left side, we're going to index 1 through m, and the top right side, we're going to index 1 through n. So now we can refer to our m rows and n rows in terms of these indices. So this row right here is called our ith n row, and the I refers to the index of the topmost vertex of that row. And similarly, this here is the jth m row, where the j refers to the index of the topmost element. And so so you'll notice that the n rows are the rows that have n elements, and the m rows are the ones that have m elements. And we have this here so you can refer to it throughout our talk. So now let's talk about linear extensions of our poset. So a linear extension of a rectangular poset is an ordering of all the elements in a way that respects our ordering relations. So an example of a linear extension of this particular poset is the one where you select all the elements in order, in the numerical order that we've labeled the vertices. So we start with the 1 because all of the elements are above it, and we can continue on, and we've given it kind of a random numbering, but we end up with a linear extension that obeys the partial ordering. So in this case, we numbered them in a way to help illustrate what a linear extension can look like. But in our discussion, we'll be giving our posets a set numbering, and we'll be talking about, we'll be writing our linear extensions in terms of the set numberings that we give them. So we'll talk a little bit more about that in a minute. But an example of a linear extension of this numbering here, which is one of the ones we'll be looking at, is this up here, 1, 5, 9, and so on. So we start at the bottom with the 1, and at this point we can either choose the 2 or the 5. So we went with the 5, and from here we can go to the 2 or the 9. We went with the 9, and so on. So notice that when we give our poset integer labels 1 through mn, we're able to represent our linear extensions as a permutation. And when we do that, we represent our linear extension as a permutation, we can consider some of their combinatorial properties, such as pattern avoidance, which now Ruth will talk about.